Thank you, Krishna. It's my great pleasure to come again to the University of Connecticut. I'll talk about dynamic programming and material based on a research monograph that is about to be published. It's already online and it's about to, a print edition is about to go to circulate. And the first edition of this monograph was done in 2013. And since that time, I've done a lot of work, and it's time to do a second edition. I'll explain what abstract dynamic programming is as we go. However, I'm going to introduce the subject in terms of an application that most of you are familiar with, which is deterministic optimal control and issues that relate optimality and stability. Okay, dynamic programming is a universal methodology for sequential decision making. And it applies to a very broad range of problems, spanning the field from deterministic to stochastic, and also from combinatorial problems with finite state space to optimal control problems with infinite state and control spaces. Dynamic programming became quite popular with new developments in dealing with approximations. About maybe 20, 25 years ago, approximate dynamic programming or synonyms like neurodynamic programming, reinforcement learning, and perhaps others. So the classical difficulty with dynamic programming is the curse of dimensionality. You could only solve exactly small problems, but if you properly use approximations, it's possible to solve much larger scale problems, which can be very challenging. And by now, the methodology has proved itself in many fields, including some high-profile successes. They're quite spectacular, like the method that learned how to play Go at the level of the best humans received a lot of publicity, the AlphaGo program. Now, the standard theory of dynamic programming, there's theory for exact dynamic programming and approximate dynamic programming. I'm going to focus on exact dynamic programming. And the standard theory involves analysis of Bellman's equations, the solutions, how many solutions there are, whether they exist, and so on, and conditions for optimality. And there are also issues around algorithms, and the standard algorithms are value iteration, policy iteration, and the approximations are typically based on value and policy iteration. Now, abstract dynamic programming aims to unify the theory through mathematical abstraction. There are many dynamic programming words because the methodology is so general. It applies deterministic, stochastic, minimax, combinatorial. However, one nice thing about dynamic programming is that its theory can be developed in generality, and so you don't have to deal with specific models with very precise assumptions. You can develop the theory in a much broader context and then specialize to particular models. Now, semicontractive dynamic programming is an important special case of abstract dynamic programming. I'll explain what that is later. And it's the focus of most of my research. Okay, so I'm going to start first with a classical application that deals with deterministic optimal control, classical issues of optimality and stability, whether an optimal policy is stable and vice versa. Then I'm going to summarize the main results and try to explain them. Then I'm going to extend the analysis to stochastic optimal control and stochastic shortest path problems. Then I'm going to get into a generalization, which is abstract dynamic programming, and how this particular application fits into the framework, and then talk about semicontractive dynamic programming at the end. Okay. So here's the problem I want to start with. It's a classical deterministic discrete time optimal control problem. You have a system which state at time k is denoted xk, the control at time k is denoted uk. It must satisfy certain constraint that depends on the state. And there is this system equation here relating how it relates the next state at time k plus 1 with the current state and the control uk. We're interested in policies which are feedback control functions, a sequence of these mu's. They take the current state, which is observed with certainty, and they map it into a control. And we want to look at policies, sequences of functions like this. We want to look at non-stationary sequences for reasons that have to do with for theoretical reasons. And we want to optimize over those. And what is the optimization criteria? Okay, we will assume here that the cost per stage. At each stage, you incur a cost g of x and u, where x is the current state and the current control. There is also, we assume, a destination state, basically a state that you want to go to, roughly speaking. It is cost-free. If you are at that destination state, you stay there. Think of the zero state or some kind of a reference state that you want to be in. And it is also absorbing. Once you get there, you stay there. Okay? And now, given this cost per stage, and given a policy and an initial state, there's a sequence of states and controls that's generated. At stage J, we have this cost incurred. We sum up all the costs from 0 to infinity, and that becomes the cost of policy phi starting at state x0. Okay, so we want to optimize over phi. So J star of x0 is the minimum of this cost over phi. Okay, so that's the definition of J stars of x, the optimal cost starting from state x. It's a function over the state space. And that's what we want to find, and also an optimal policy, a policy that attains the minimum here. Okay, so this is a very classical problem. It's simple in some sense because it's deterministic, but also it has some fascinating complications that have not been fully worked at. Two characteristics of this problem, in addition to the destination, is that it is very general. The control space is arbitrary and the state space is arbitrary. So a special case is an optimal control or regulation problem where the destination is the state that you want to reach and stay around. Or it includes also shortest path problems with finite number of nodes or with an arbitrary state space. So it's a very, very general problem within the confines of deterministic dynamic problems. A classical example is the linear quadratic regulator problem. The destination state is 0. You have a linear system defined by matrices A and B, and the cost per stage is quadratic. A quadratic with a positive semi-definite matrix Q, and a quadratic from the control with a positive semi-definite matrix R. And roughly speaking, here you have a linear system. You want to bring it down to the origin with a minimum cost. Very important problem. And let me try now to make a connection between optimality and stability. Control engineers are not so much interested in optimality. They are interested primarily in getting a stable controller. That's the paramount importance in control system design. And basically, a stable policy is one that drives the state to the destination through control over an infinite horizon, either asymptotically or perhaps in a finite number of steps. Many different this is a loose definition, and many different definitions of stability, bounded output stability, asymptotic stability, hyperstability, and so on. There are a lot of different versions of stability. Stability was a very hot subject for a long time. When I first started in graduate school at MIT, at the laboratory where I'm at now, about 1/3 of the research in the laboratory was on stability. How to design stable controllers. There were some prominent faculty members at that time there. There were some some hotshot students, and they were doing great research. Another third of the research that was going on at that time was optimal control. Mike Athens was there, and there was a lot of activity in that area. It was an emerging subject then. Now optimization has become a universal tool, but at that time it was emerging. And one of the motivations for optimization and optimal control was to design stable controllers through the computational methodology of optimization. And a basic idea here is that trajectories x of k generated by an optimal policy drive the optimal cost to zero. You can actually prove that. So J star, the optimal cost function, can be viewed as a sort of Lyapunov function for the system. On the other hand, an optimal controller is not necessarily a stable controller. And this was pointed out, among others, by Kalman in his fundamental 1960 paper, where he introduced controllability and observability in the context of the linear quadratic regulator problem. In fact, Kalman's motivation, to a great extent, for controllability and observability was to provide conditions under which a solution, an optimal controller in the classical regulator context, was also stable. Okay, so let's leave this here, and we are going to return to this point a little later. Let's talk about the classical dynamic programming theory for non-negative cost problems. Remember, our cost per stage is non-negative. This theory goes back to the 60s, and the first major result is that J star, the optimal cost function, solves Bellman's equation. Okay, this is Bellman's equation. It expresses the principle of optimality. The optimal cost starting at state k is obtained by considering the first stage cost plus the cost to go from the next state, minimizing overall controls here. Now at the destination, we have that the optimal cost is zero, so this is part of Bellman's equation for our problem. And there's an equation like this for every state, right? And so we're looking for, this is a functional equation, satisfied by functions j of x, and this equation has as a solution J star, but it may have other solutions as well. However, J star is the smallest non-negative solution out of all solutions. That's part of the classical theory. Also, if you can solve this Bellman equation and minimize over here for every x, and piece together all the minima to a feedback control function, this mu star that claims the minimum for every x is optimal. And that's also part of the theory. There is also the value iteration algorithm. Now, the value iteration algorithm iterates with this dynamic programming mapping, starting from some initial condition j sub 0, and it generates j sub 1, j2, and so on in this way. And under some conditions, not always, under some conditions, if the value iteration algorithm is started from below J star, then it converges to J star. Usually this is satisfied. If the control space is finite, for example, is satisfied. However, if you start value iteration from above J star, it may get stuck. For example, it may get stuck in some of these other solutions of Bellman equation. If you started at a solution of Bellman's equation, value iteration will stay there. So value iteration is a little flaky for our problem. Also, the other major algorithm, policy iteration, about which I'm not going to say very much, is also erratic. It's possible for policy iteration to oscillate and not to converge to an optimal policy. So there are some gaps here in the theory, and these gaps are quite real. And let me now get back to the linear quadratic example. Okay, here I'm considering a one-dimensional example. The termination state is 0. The system is what you see here. It's a linear system involving a coefficient gamma, and this gamma is greater than 1. So this system is unstable. It's driven by control, but if you don't apply any control, then the state just goes off to infinity. Now the cost per stage here I'm taking to be just the square of the control. So there's no penalty on the state. Okay? So what's the optimal policy? Well, the optimal policy is to do nothing. Apply control u equals 0 at every step. In which case, the optimal cost will also be 0 because there'll be no cost that incurred at any stage. However, if you apply no control, then the closed loop system that you obtain is not stable. Okay? So an optimal policy is not necessarily stable. And this is an example of this happening. Okay, so now let's look at the solution of these linear quadratic problems in the context of this simple special case. The Bellman equation gives rise to what's called the Riccati equation. And the Riccati equation is a matrix discrete time equation. In this particular case, it's a scalar equation. And the Riccati equation for this problem takes this form. It's a quadratic equation in P, right? And you can plot the solution of this equation, as I have done here. If I plot the right-hand side, I get this red curve over here. If I plot the left-hand side, which is P, it's just this straight line. And the points where the right-hand side is equal to the left-hand side, you get the solutions of the Riccati equation. And J star, or P star rather, corresponding to the optimal cost, is a solution. It's the smallest solution, in fact. But there is also another solution over here, which I call P hat. It's gamma squared minus 1. You can calculate it. And what is this solution here? It turns out that this second solution is the optimal cost of a restricted problem, restricted over just the stable policies. In other words, if you minimize, instead of all policies, consider just the stable policies, then the optimal cost function that we get is this J hat here. And it's different than J star, and moreover, if you apply value iteration is abstracted to this J hat rather than to J star. And you can see this from this figure. Value iteration translated in the context of the Riccati equation, you start with some initial P, and go over here, you get P1, then go over here, P2, and so on. From any starting point, you converge to P hat, except if you start from P star equals 0, in which case you stay at P star equals 0. So you have this situation where there's an optimal cost, and there are some other costs that have some significance, they are restricted optima, and a classical algorithm like value iteration and also policy iteration in this example converges to the J hat solution, not to the optimal solution. Okay, so I'm going to try to address this anomaly and see how we can generalize it and how we can deal with it. Now we note here that the cost per stage does not depend on the state. In fact, this is what creates the difficulty. So this gives rise to a stabilization idea. Add a little stability objective, delta x squared to the u squared, so that you provide an incentive for the state to be driven towards 0, and you have an incentive for stable control. Then, for every delta, there is a corresponding problem whose optimal cost function is J stars of delta, and it has this form here, with P stars of delta being the solution of the Riccati equation corresponding to this delta. There's another plus delta over here, and it turns out that there's a unique solution in that case. Because here the classical observability and controllability conditions of Kalman's are satisfied. However, for small delta, as you drive delta to 0, take the limit, then you obtain p hat. And the reason is that if you introduce this delta here, the unstable policy, which is optimal, doesn't matter anymore. Immediately, its cost is driven to infinity and basically disappears from the picture. So P star delta involves, expresses what can be achieved with stable policies and not with unstable policies, and that's the reason why you get in the limit as delta goes to 0, P hat, and not P star. Okay, so now let's look at the stabilization idea a little more closely and try to relate stability and optimality.
So if you're putting a constraint that P should be positive definite, would that have solved the problem too?
Yes, if the cost per stage involved a positive definite term on the state, this would have solved the problem. And however, it may be meaningful to have zero cost on the state, because this will distort the cost function. Suppose you are interested to find a minimum energy stable controller. That's the formulation that you would prefer. Okay. But I'm not presenting this necessarily as a significant problem from the point of view of applications. I'm just giving this to you to give you an idea of what the theory involves and what are the exceptions that can occur. Okay, so I'm going to summarize the analysis. I'm not going to give you the details, proofs, and so on. I'm going to give you the results and try to explain it in an intuitive way. You have a question?
Yeah. Are we always assuming that you're moving in the positive direction? There is no way in going backwards in the system?
The system goes from xk to xk plus 1. Cannot go to xk minus 1. No. No, the time is one directional. Yes. Okay. So now the first idea is to add a small perturbation to the cost function in order to promote stability. And so we add to G a delta multiple of some function P, a forcing function P that forces the state towards 0. It's positive for x different. Forces the state towards the destination. It's positive for x different than the destination, and it's 0 at 0. So now, the perturbed cost function, after you add this perturbation, is the cost of the policy, the ordinary cost of the policy, plus the extra cost of the perturbation, which is delta times the sum of the p's. And this is the stability objective, this is the cost objective, and this is the stability objective, and we combine them with a delta here. And we say that a policy is pi is p stable if this combined objective is finite, which is equivalent to saying that both of this is finite and this is finite. So in particular, the definition of stability is independent of delta. It's true for every delta, okay? Every positive delta. So that's the definition of p stability. And what is the role of this p? Well, first of all, it ensures that the p-stable policies drive xk to 0. This has to happen because p-stable means that this sum is finite, so the tail of the sum must go to 0. The other thing is that the choice of p differentiates stable policies by speed of stability. Not all p-stable policies are the same. Some are faster than others, and it depends on p. So, for example, if p is the absolute value of p, is the norm, then this is a faster controller than a controller that's based on this. Okay? Of course, you could have a controller that's stable with respect to both. But if one is stable with respect to one and respect to the other, this is the faster one. Now, if not all p-stable policies are created equal, is there a most stable policy? And And this is obtained by taking the perturbation to be equal to 1. And this perturbation is special because then the corresponding p-stable policies are the policies that terminate. In order for this thing here, this sum, to be finite, when p is equal to 1, this sum has to involve a finite number of non-zero terms, which exactly means that a p-stable policy with respect to this forcing function must be terminated. It must reach t in a finite number of steps for all x0 for which this is possible. And now the terminating policies are the most stable. If you have a terminating policy, it is stable with respect to every p. So they are at the core of all this hierarchy of p-stable policies. Okay, so now let me give you a summary of the results. I've drawn here schematically J, here's J star, and let's call J hat P the restricted optimal cost over just the p-stable policies, starting with x. And let's plot here also J plus of x, the optimal cost over just the terminating policies. Then we have that J plus is greater than J hat P and J star because this is a minimum over a smaller set of policies, and this is generally smaller than all of those. So these three things ought to line the line like this. They are aligned. J star is the smallest, J hat P is in the middle, and J plus is the largest one. And the important result here is that all of these are solutions of Bellman's equation, and all solutions of Bellman's equation lie in here. In other words, J plus is the upper bound to all solutions, and J star is the lower bound of all solutions. Moreover, there's another result here. Value iteration converges to J star if it's started from above. Okay? Value iteration starting from somewhere in the middle converges to J hat P from some special region of Lyapunov functions corresponding to P. And so you have these regions of convergence of value iteration, and the region that corresponds to J plus is interesting because it's characterized more easily. Okay, now why should this result be correct? Why is J hat P a solution of Bellman's equation? Well, in the delta perturb problem corresponding to a forcing function P, the P unstable policies cannot be optimal. Basically, they get infinite costs, so they disappear from the picture. So J hat P reflects only the P stable policies. The P unstable policies do not matter. So what we have is that this is the optimal cost over the stable policies with a delta perturbation, and as delta goes to 0, we have this result here. Now, this thing, the optimal cost function of the delta perturb problem, solves the perturbed Bellman equation, which involves, it's just a regular equation with just a little delta. Take delta to go to 0 in the limit, and you get that J hat P is a solution of Bellman's equation. It's a proof that requires some care to do it right, but it's also intuitively clear why this result should be. Create a perturbation, the perturbed problem solves, the optimal cost function thus solves Bellman's equation, take the limit, and you get that this also solves the original Bellman equation. Okay, now here there are favorable cases and not so favorable cases. The favorable case is when these two upper and lower bound coincide, when J star is equal to J plus. And this often holds. Basically, this happens if the policies that achieve controllability can get you in a finite number of steps to the destination, if these policies can be arbitrarily close to optimal. If you take the infimum over terminating policies, you get the infimum over all policies. And this is a common situation. Now, if this happens from this diagram here, we see that there's a unique solution to Bellman's equation, and this is J star. Moreover, the optimal policy is P stable for every P. Okay? In fact, there exists an arbitrarily close to optimal terminating policy that achieves controllability. There's also this result here, that value iteration converges to J star from above. Policy iteration also converges to J star from above, and usually, under some minor additional condition, they converge from starting from every policy and every J that's non-negative. So, nice results hold in this favorable case. And I'm illustrating here the result here. It's a schematic, two-dimensional image, the diagram of cost functions. Here's J star. It's the unique solution of Bellman's equation in this favorable case. And the paths of value iteration all go from anywhere in this quadrant, they go to J star. So that's what this says. Value iteration converges from above, and usually under my conditions from below. The optimal policies are P stable. There's also linear programming approach for computing J star also works because of a result that you can prove here. So all the results that you would like to be true hold in this favorable case. Now let's go to the unfavorable case. The unfavorable case is when J star is different than J plus. Again, this is a two-dimensional picture, kind of schematic. The red set here is the set of solutions of Bellman's equation. I've drawn it here arbitrarily. In some cases, in special cases, it has special structure. There's an upper bound to all of these solutions, J hat plus. It's a lower bound. So everything lies between these two, component-wise. If you go to J hat plus, this set of starting points for value iterations give you convergence. So no matter where you start, above J plus, you converge to J plus. And for any other solution, J hat P prime for two different P and P prime, J star, there's a region of convergence of value iteration. And this region is the set of functions lying above the corresponding restricted optimal over P stable policies, and drive and their values are driven to zero for all the P stable along the trajectories generated by P stable policies. So you have J hat P, and consider functions J such that if you use a P stable policy and start from consider the points from which the value of J xk goes to zero. Consider all of these starting points, and this is the region of convergence of value iteration for this solution. There's another region, non-overlapping, to another solution here, and for J plus, you have a particularly favorable region of convergence. And this region of convergence can be viewed as a set of Lyapunov functions for the P stable policies. And the definition is over here. Okay, so that's in summary all of the analysis. And let me demonstrate this analysis in terms of a very, very simple example. This is the simplest dynamic programming problem that you will ever encounter. It's a shortest path problem, deterministic, with just one node and a destination. And at this node, you have a choice of staying there at cost zero, or move to the destination with a positive cost. Okay? So what is Bellman's equation? Bellman's equation is what you see here. J is of 1, there's only one x that has its values at question. It satisfies this equation here, and J is 0. The optimal cost is 0. It is optimal to spin around forever in this cycle. This is a problem with zero-length cycles, which are known to cause problems in shortest path knowledge. And, however, what are the stable policies? The stable policies, there's only one of them, the one that goes straight to the destination, the terminating policy. So J plus is equal to B, the cost of that terminating policy. Now, looking at solutions of Bellman's equation with J equals 0, on this axis, here is J plus, here is J star. If you look at the solutions of Bellman equation, there are all of these points here. The non-negative solutions are just the ones in this interval. There's an infinite number of solutions. The ones that correspond to stable policies are this one. This corresponds to an unstable policy. This corresponds to no policy at all, actually. Okay? It's just intermediate, spurious solutions of Bellman's equation. And how about value iteration? If you start value iteration from above, then you're going to converge in a single step to this. If you start Bellman's equation from any one of these red points, you stay there. If you start, then the only way you can get to J star is to start at J star. Value iteration is completely useless here. And if you try to add a perturbation to this, then you're going to pick up this point and not that point. Okay, so that's the summary of the theory for deterministic problems. And now let's talk about stochastic problems. I have one slide for this. Here, Bellman's equation involves an expectation. The system function involves also a stochastic disturbance W. So the next state depends on the current state, the control, and the stochastic disturbance. And Bellman's equation is what you see here. Again, it expresses the principle of optimality. Okay, this is an important problem now. We still have a destination. This is an important problem that arises in many, many contexts. Problems of routing, of path planning, problems of robotics, where you try to reach a goal at minimum cost, but there is uncertainty. And the problem has a long history in many applications, particularly for the finite state case. The infinite state case is quite unexplored, actually. And assume a finite number of states now. The analog of a terminating policy is what's called a proper policy. A proper policy, by definition, is one that leads to the destination with probability 1 from all states. So you start at some state, you choose a control, you can go to any number of next states according to the probability distribution of W. Then again, so the state spins around according to a stochastic process, a Markov chain for every policy, and the proper policies are the ones that you are guaranteed with probability 1 to reach the destination, no matter where you start. It's a fundamental concept in stochastic shortest path problems. Now let's call J plus the optimal cost over just the proper policies. Okay? It doesn't have to be equal to J star. Now, the case where the two are equal was investigated back, well, there are a number of authors before us, but the strongest results, I think, are in this paper here. And these results, among others, say that if every improper policy has infinite cost from some initial state, then J star is equal to J plus, and it solves uniquely Bellman's equation. Moreover, value iteration converges to J star for any starting point that's not negative. So to see an application of this result in a familiar context, think of a deterministic shortest path problem where every cycle has strictly positive length. Then these cycles don't matter, optimal policies do not cycle, so you're getting the optimal cost is equal to the restricted optimal cost over the policies that drive you to the destination, and you have all the standard and familiar and powerful results for that case. If, on the other hand, you have zero length cycles, then you can get phenomena like the one I illustrated earlier with my one state example. Now, this case was investigated just recently in a paper with my collaborator Jenny Yu, and we showed that J star and J plus are the smallest and largest solutions of Bellman's equation. Moreover, value iteration converges to J plus starting from any J greater than J plus. Now, the case where you have an infinite number of states, there is research on that, and the latest is a paper that I've written a few months ago. The theory is not as powerful as for the finite state case. It involves some assumptions that correspond to boundedness of some cost. In particular, if the cost per stage is bounded, then let's redefine a proper policy to be one that reaches the destination in a bounded except expected number of steps, like rather than a finite number of steps like before. And let's call J hat the optimal cost over just the proper policies. Then the result is that J star and J plus are the smallest and largest solutions of Bellman equation within the class of bounded functions. That's sort of bothersome because actually there may be some unbounded functions above J plus. So it's a complicated picture in this case, and there's a fundamental difference between deterministic shortest path problems and stochastic shortest path problems. The structure of the solutions of Bellman's equation is different. You also have a value iteration result for this. Okay, so here's where we stand in deterministic shortest path problems with infinite state space, and with stochastic shortest path problems. And now let's try to generalize on this and show and illustrate how the results that I've given you manifest themselves within a broader context of an abstract dynamic program. Okay, so what is abstraction in mathematics and what can it do for us? According to Wikipedia, the source of all knowledge nowadays, here's a definition. Wikipedia has it right. I like this definition. It says that abstraction in mathematics is the process of extracting the underlying essence of a mathematical concept, removing any dependence on real-world objects with which it might have been connected. No applications when it comes to abstraction. Generalizing, because applications actually confuse us within this abstract context. Generalizing the concept so that they have wider applicability or they match among other descriptions of equivalent phenomena. So abstraction allows us to look at the picture without any clutter of assumptions that are unnecessary, reference to particular applications, and so on. Now, Wikipedia goes on and says that, and mentions the advantages of abstraction. It reveals deep connections between different areas of mathematics. Known results in one area can suggest conjectures in a related area. Techniques and methods from one area can be applied to prove results in a related area. So in a nutshell, we eliminate the clutter and let the fundamentals stand out. And that's our objective here. Now, the first question that comes to mind is, what is fundamental in dynamic programming? And if you are even moderately familiar with dynamic programming, the answer is quite evident. The Bellman equation operator is fundamental. All the results, computational or analytical, are expressed in terms of the right-hand side of Bellman's equation. So that's a prime candidate to abstract, and that's what we do here. We define a general model in terms of an abstract mapping that depends on state, control, and some cost function. And then Bellman's equation for the optimal cost becomes like this. And in special cases, it takes specific forms, like in deterministic optimal control. It takes this form that we have seen. In stochastic optimal control, it takes this form here. Alpha here is a discount factor, and W is some stochastic disturbance. There are also other examples, minimax problems, where instead of an expectation, you have a maximum over some disturbance that takes values in a certain set. Semi-Markov problems, which involve special type of disturbances. Multiplicative cost problems or exponential risk-sensitive costs also come in this category, and they involve some other types of operator of abstract mapping H. Now, the key premise of this approach is that H is the mathematical signature of the problem. It includes everything that you need to know about the problem, like the cost of stage, the system function, stochastics, and so on. And it also can be used to express all the results about the problem. So it is important to look for fundamental properties of the structure of H, and the fundamental property is monotonicity. Monotonicity means that if you increase J uniformly, then this operator also increases uniformly. This is always true in dynamic programming. Contraction of this operator here is also an important property. It may be true for some problems, but not for others. So these are the two main properties of abstract dynamic programming mappings, monotonicity and contraction. And we make various assumptions about contraction, and from the mathematical signature, we obtain general methods and analytical results, and then specialize particular problems like deterministic optimal control, stochastic, min-max, whatever. So top-down development. Okay, so let's formulate this problem a little more precisely. We introduce state and control spaces, arbitrary. Okay, they could be finite, infinite, whatever. We introduce a control constraint. We introduce stationary policies, which are mappings from state to control that satisfy the constraint. And we introduce an abstract monotone mapping, H, with this monotonicity property. If J prime is greater than J, then H of H uj prime is greater than H x uj for all x and u. It's satisfied in dynamic programming, typically, as I mentioned. Okay, E sub x stands for the set of all functions that are extended real time in state. So J is a function of state, but we're allowed to take the value plus or minus infinity. And we introduce for every control function mu, we introduce this mapping T mu sub T mu. It takes functions J and maps them into other functions, T mu sub J. So this is the dynamic programming mapping corresponding to this policy. And we also define the minimum mapping, T, that takes J's into T sub J's. And this is the dynamic programming operator that comes into Bellman's equation. So our problem is going to be defined in terms of these two mappings here. And it is properties of these two mappings that determine what kind of results that you can get. We introduce some initial function, J bar, and we define the cost function of a policy. A policy is a sequence of control functions. We introduce this expression here, and we take the limit as n goes to infinity. And the problem is to find J star, which is the minimum over all pi, and not just pi. Now, let's try to interpret this expression here. This is important to understand what this means. This expression here is the cost of starting at x0, using pi for n stages, and then incurring a terminal cost J bar at the state xn. Okay? So these are finite horizon costs with this j bar as a terminal cost function, and the limit of this is the infinite horizon cost of our abstract dynamic programming problem. Now, the theory revolves around fixed properties of T mu and T, which can be viewed as Bellman's equation. There's a Bellman equation for a policy mu and a Bellman equation for the optimal policy. And we want to ask questions like, is J star the unique solution of this equation, and how to calculate it, and what are the algorithms that we can use? And these are value iteration and policy iteration type algorithms, which can be viewed essentially as special cases of fixed point algorithms. Abstract dynamic programming is really, from a mathematician's point of view, it's a special case of fixed point theory. That's what you just make special assumptions like monotonicity, contraction, and so on, and you explore the implications both at the abstract level and also for specific special cases. Okay, so as an outline, the principal types of abstract models, there are three in my view. There are the contractive models, which are patterned after the discounted optimal control problems with bounded cost per stage. These are the easiest dynamic programming problems. Then the dynamic programming mappings, the TMUs, are contractions. All mappings TMU are contractions. That's the assumption for contractive models. And the analysis of those goes way back to an important paper from 1967 by DiNardo, gave the first formulation, the first result for contractive models. Another class of important models are the monotone increasing and monotone decreasing models, where J bar has the property that Tj goes up from J. T sub J bar is greater than J bar. So value iteration sort of increasing or decreasing. This corresponds to non-positive and non-negative cost per stage dynamic programming. Here we don't make any contraction assumptions, just monotonicity of TU. And the analysis of those is quite old, it goes to the 70s. The new class of problems on which much of my monograph is focused on is semicontractive models, which are patterned after control problems with a goal state or a destination, shortest path problems, stochastic shortest path problems. Then what's happening here is that some policies are well behaved, like they terminate, they're proper, okay? They're contractive-like. In fact, you can define them as contractive in some form, while other policies are not well behaved. And the focus is, however, on optimization over just the well-behaved policies. Like in deterministic optimal control, we're optimizing over the stable policies. They are the ones that are well behaved in this particular policy. So these are examples of well-behaved policies, stable policies in deterministic optimal control, proper policies in stochastic shortest path problems, and the focus is on restricted optimization over the well-behaved policies. Okay, so now all of this is very abstract, and what I'd like to do is focus on specific results for semicontractive dynamic programming. And what's the line of analysis for this? This is only a summary. It's a line of analysis for semicontractive dynamic programming. We introduce a class of well-behaved policies, and there's a mathematical name for those. They're called regular. Define a restricted optimization problem over just the regular policies. Show that the restricted problem has nice theoretical and algorithmic properties, like the problem of optimization of a stable policy that I showed earlier. Relate the restricted problem to the original, in terms of the structural Bellman's equation, and the reasonable conditions obtain interesting theoretical and algorithmic results. Under favorable conditions, like when the optimal cost of the regular policy is equal to the optimal cost, then you obtain powerful analytical and algorithmic results, comparable to those for the contractive models. So there is a silver lining to all this. It's a mathematical complication, but there's a favorable class of problems. If you formulate your problem so that these favorable conditions are satisfied, you get great results. But it's also important to understand what happens under conditions that are not so favorable. So I'm going to try to explain in pictures what the situation is under these two types of conditions. What do we mean by regularity? Well, regularity involves a set of functions, S. And we say that a collection of policy state pairs is S regular if this equation holds for every J in S. In other words, if in the finite horizon cost corresponding to the policy, you change the terminal cost from J bar to J within S, then there's no change. Now, what I've written here, change the terminal cost function J bar to any J does not matter in the definition of J bar. Basically, the state policies are the ones that are well behaved. Basically, the S regular policies are the ones that are well behaved with respect to value iteration, as long as you start value iteration from the set S. Okay. In terms of our optimal control example, let's take S to be the non-negative functions, that is 0 at the destination. Then the set of all terminating policy state pairs is S regular. And we define for a given set C that is S regular, we define the restricted optimal cost function with respect to C. This is like defining the optimum over the proper policies or the state policies. Okay, so now what we're going to show is that this has good fixed point properties, and we're going to relate it to the optimal cost function. And here's a basic theorem. It is not a difficult theorem to prove, but it is a tricky theorem to conjecture, to just figure it out that this theorem should be true. Because it has a bit of a strange structure. It says that if you have a collection C of S regular policy state pairs, then J stars of C, the restricted optimal cost function, demarcates the space of all J in two parts. One is the well-behaved region for which J is above J stars of C, but below some J tilde in S. And the other is a different region where all the fixed points lie. In other words, this J stars of C, if C is S regular, puts a bound on, separates out the set of fixed points and solutions of Bellman's equation. They all lie below J stars of C. Moreover, if you start value iteration from every point in this well-behaved region, you end up below here. So what happens if this J star C is a fixed point of T, is a solution of Bellman's equation, then you get convergence to J stars. So that's a key result. The limits of value iteration starting from this well-behaved region lie below J stars of C and above all fixed points of T. So let's visualize this result. A two-dimensional, yes.
Why are the limit? So the limit doesn't exist. So you take limit infimum and limit supremum. Why
Yeah, the limit doesn't necessarily exist. It can be, in fact, it may be minus infinity. In fact, or it makes the T case of J does not go down monotonically. Okay, that's not necessary. Once it starts going down monotonically, then it will go down. But in general, the two can be different. Okay, this is a figure that relates to the case where J stars of C is not a fixed point, but S is the entire space. Okay. So the well-behaved region is whatever lies above J stars of C. Now, according to the theorem I just gave you, all the fixed points of T lie below J stars of T, and the limits of value iteration are in this red region, demarcated from JC star from above and from the largest fixed point of T from below. Okay. So from the well-behaved region, we go to the limit region with value iteration, and all fixed points of T lie below J stars. Now this is a more complicated figure for another case. Here we assume that J star is a fixed point of T. So this is the largest fixed point. And the well-behaved region now is a little bit more complicated because S is not equal to the entire space. I've drawn S to be this set here. So the well-behaved region is the blue region here. And there may exist some fixed points also that are outside this, okay? Before we had S be the entire space. But there may exist some fixed points that are outside. The value iteration now has the property that if you start it within this blue region, you will converge to J stars of C. All of these are simple consequences of this one theorem that I gave. And there are some, if you work several special cases, very special cases here, you'll see that some very interesting phenomena happen that you wouldn't expect. Okay. So, in particular, if this region here is unbounded from above, J star, these fixed points do not exist, and J stars of C is a maximal fixed point of C. And you have convergence from above of value iteration. Okay. So now, one slide to make the relation back to the deterministic optimal control. In the deterministic optimal control, we'll let this be the set S, and we consider this collection of policy state pairs such that this policy terminates starting from the state. Then it's easy to show that this C is S regular because the terminal cost function does not matter for a policy that terminates. The terminal cost is going to be 0. And the general theory apply. J star and J stars of C, which is what I told earlier, J plus, are the smallest and largest solutions of Bellman's equation. Value iteration converges from above to J plus, and there are other results also that pretty much follow from one theorem that I gave earlier, but with embellishments for this particular special case. There's also a corresponding result that relates to p-state policies. If you define this collection PSC, and then you define S in a more complicated way to be the set of Lyapunov functions of the p-state policies, then this is S regular, and the results that I gave earlier. Now there are similar applications to various other types of dynamic programming problems. Discounted and undiscounted stochastic optimal control, minimax problems involving maximization over disturbance, robust shortest path planning. This is an area where I have done some work and applied semicontractive ideas, which is minimax shortest path problems, multiplicative cost problems, where the Bellman equation mapping is like this. Here J bar is identically 0, the terminal cost. Here the terminal cost is 1, identically 1. Okay? So you start from 1 and the cost accumulates multiplicatively over an infinite horizon. A special case of multiplicative cost is exponential, an exponential cost function, and it has this form here. This problem introduced some risk sensitivity, whereby we prefer smaller costs over larger costs. we take into account. We want basically small variance, of course, and this biases the optimization towards smaller cost. Small cost functions. Okay, there's more here. The research monograph deals with all kinds of special cases of applications of these results. So let me conclude here. I talked about specific results in deterministic optimal control, a connection between stability and optimality, forcing functions, perturbed optimization, and the notion of P stability, which quantifies the speed of stability as well. Connection solutions of Bellman's equation with P-Lyapunov functions and regions of convergence of value iteration. There are also value and positive policy iteration algorithms for computing the restricted optimum over state policies. For the general model, the idea is, again, to streamline the theory through abstraction, develop results in generality, and then specialize. The notion of S regularity lies at the heart of this semi-contractive models. It deals with restricted optimization over the S-regular policy state pairs. Through these ideas, we localize a set of solutions of Bellman's equation. We place bounds on it and improve uniqueness if possible. And we also localize the limits of value iteration and policy iteration. And there are favorable cases where everything works out very nicely, and not so favorable cases where the results are more complicated. And while the theory is abstract and kind of mathematical, it has a very broad range of applications. Because these problems that involve a termination state are prevalent. They're in robotics, in planning, all sorts of very hot applications these days. Okay, so that's the end of my talk.